Alright, problem 4 is Osborne on a train. So let's do 4. That's Osborne on a train. So the thing is that, like, you're standing on the ground here, right? Osborne is on his train. So the velocity of the train with respect to the ground is given as 10 meters per second, or the speed is given. I'm going to hold off on turning it into a velocity, and I'll show you why in a minute. And Osborne is standing here. There's his little ponytail, and he throws a ball at a 60-degree angle relative to him. So 6 degrees above the horizontal relative to him, and you've got to figure out. So we can say, I don't know, velocity of ball relative to train initially at 60 degrees. You don't know what it is, but you don't know the magnitude of it, but you know the direction of 60 degrees. So, and what happens to you is that the ball appears to just go, as he does this as you pass by, let's say, so the ball appears to you to just go vertically. So to you, the ball appears to go vertically. So what we can say is the velocity of the ball with respect to ground in the x direction equals 0. So, first of all, we want to know which way the ball is going. Well, now if you think about this, or sorry, not which way the ball is going, which way the train is going. So really the question is Osborne throwing toward the front of the train or toward the back of the train? And so if you think about this, it's not very hard to think this through just intuitively. Here's the train. There's Osborne on his train. If the train is going this way and he throws it this way up, there's really no way the ball could look like it's going up and down, because if he's just holding the ball, it already looks to you like it's moving this way. And if he throws it forward, then it's just going faster that way, right? So what really has to happen is that the train has to be moving this way while Osborne throws it this way, so that the horizontal component of his throw cancels out the velocity of the train and leaves the ball just going up and down. And so keep in mind, Osborne continues to move to the left, so it looks to him as though the ball is moving through a parabola. To you, the ball is just going up and down. So once you get that figured out, it's pretty easy. So we're going to say velocity of the train with respect to ground equals negative 10 I hat meters per second. So we're just going to do the standard frame where you got y vertically and x horizontally, as people like to do. Okay, and then the velocity of the ball in the ground frame equals, well, it's all y direction, so VBG j hat. Okay, and then what else do we know? So we know basically that Osborne threw the ball at 60 degrees relative to him. So what's the velocity of the ball? Let's see, velocity, that's a vector. So that's the velocity of the ball relative to the ground, and the velocity of the ball relative to the train, we don't really know what that vector is, but we can figure it out. So remember, again, John Coley notation, or whoever, he probably didn't invent it first, but I think of it that way because that's the book we read it out of in my class. But the vector velocity of ball with respect to train with respect to ground, and ball with respect to the ground. So you look at these three you have, figure out which way you can make an addition from them, and that is to take BT and TG. So velocity of the ball with respect to the train plus velocity of the train with respect to the ground equals the velocity of the ball with respect to the ground, right? Okay, so velocity of ball with respect to the train, we don't know. Ball with respect to train, but we do know that train with respect to the ground is negative 10 I hat meters per second. And we know that the velocity of the ball with respect to the ground is purely vertical. Okay? So really what this tells us, there we go. Velocity of the ball with respect to the train equals positive 10 I hat. We're just taking this and moving the 10 I hat to the other side. 10 I hat plus ball's velocity with respect to the ground in the j hat direction. Okay, so or ball's speed with respect to the ground in the j hat direction. The point is this is just vertical, so this just adds up nicely So here's VBT, all right, and here is our 10 I hat meters per second, and it's this plus this, so this is our VBG J hat. Okay, now what we know is that this is 60 degrees. So now it's pretty easy to figure out what VBT is and VBG. So VBT, the magnitude of VBT over 10, no, I'm sorry, magnitude of VBT times the cosine of 60 degrees. And let's see, 60 degrees equals 10 meters per second. And what that means is the initial speed of the ball with respect to the train, so this is the magnitude of this vector here, must be 20 meters per second. And then, which don't really technically even need that, but it's nice to have just to make things work. And then velocity of the ball with respect to the ground, and this is all initially, by the way, so we're going to get into how that changes for a moment. But the speed the ball is thrown with respect to the ground is then just the tangent of 60 degrees equals VBT tangent 60 degrees. Oh, sorry, actually, well, VBT times sine 60 degrees, so, but it would be, yeah, so I need to erase. Let's see, where's my eraser? There we go. So let me do, you know what? Yeah, so equals, let's just do this sort of the easier way. So this is 10, right? 10 times tangent of 60 degrees, okay? Tangent of 60 degrees is, hold on, tangent of 60 degrees is going to be radical 3, right? So velocity of the ball with respect to the ground is 10 radical 3 meters per second. I'm going to leave it as the radical for just a moment because that comes in handy. So now we want to find how high the ball goes. For this, see, it doesn't matter whose frame we're in because Osborne throws it up, or throws it, you know, it looks like it gets some height to Osborne, looks like it gets some height to me. We're neglecting the fact that the train is going to be a little taller than the ground. So I'm standing on a, you could say I'm standing on a stationary platform, you know, say the same height as the train, you know, if you want to look at it that way. But whatever, you know, we're not worrying about that part. So the ball, this is the initial vertical velocity of the ball. B0, I'm going to say Y. So I'm stringing 3 subscripts along. This looks incredibly ugly, but it's the ball's initial velocity with respect to the ground, really. So 4 subscripts. V, ball with respect to the ground initially in the Y direction is this. Okay, so now if an object is thrown upwards at Vy naught, I'm just going to abbreviate a little there, 10 radical 3 meters per second, how high does it go? What's the maximum h? Well, if you did your well, you know, let's just say when does the velocity equal 0? So velocity y is Vy naught minus gt. I'm actually embarrassed because I can't remember the direct formula myself, but this is good anyway. So when it's still in the air is when it reaches the top, or when it has, sorry, no y velocity is when it's reached the top of its arc, or just gone straight up and stopped here and then come back down. Either way you want to look at it. Okay, equals 10 radical 3 minus g times t. I'm going to use 10 meters per second squared for g t. So t equals square root of 3, obviously. And then how high does it go in that time? So, you know, d, or actually, let's see, delta y equals, so Vy initial times t minus 1/2 g t squared. Okay, so delta y equals, what's initial velocity in the y direction is 10 square root of 3, and then t is square root of 3, minus 1/2 times g, so g is 10, so I'm just going to use that, and then t squared is 3. Okay, so this is 10 radical 3 radical 3, this is 30, and then 10 divided by 2 is 5, times 3 is 15, minus 15. So maximum height it gets to is 15 meters. And that is how you do problem 4.